Okay, thank you everyone for joining the session. As Don mentioned, I'm a director at the JP Morgan AI research team, and the team is about 100 or so research scientists, and they come from all sorts of backgrounds. It's a very multi-talented team. But the part of the team that I'm involved in does document AI. And here are some of the key contributors to that capability within the team. So some of the work that I'll be presenting today is basically work by these guys. Now, what does Document AI stand for? I think the name is pretty descriptive already. As you can imagine at JP Morgan, on a literally daily basis, we're dealing with tens of thousands of documents. And these documents could come from any source. They could be client disclosures, tax forms, invoices, receipts, legal contracts, prospectuses, you name it. So we're collecting all these documents and we're passing them through massive operations teams whose job is basically to sit down, read them, and process them. And the types of processing that these teams do spans a very wide range of natural language processing tasks: information extraction, question answering, summarization, verification, document profiling, and so on. Now, obligatory large language model slide. In the past couple of years, there's been major improvements in the language modeling space. This was where the field stood as of April of this year. We're seeing lots of growth in that space. And then, this was March. And then already by June, the landscape had already completely shifted. We now had GPT-4. We knew some stuff allegedly about its architecture. It was outperforming all the other models and so on. So things keep changing and evolving very fast. And this isn't just something we're observing in the language modeling space. We're seeing similar trends in multimodal image and text, or speech and text spaces, in computer vision, and so on. And the outcome of these types of advances has been the fact that many of these models are either now matching or surpassing human performance on common benchmarks. And these benchmarks reflect the types of tasks that I just spoke about: information extraction, summarization, question answering, and so on. Now, does that mean that we're done? That we could basically use these models, plug them into our operational workflows, we automate everything end to end, and we're good to go? And I argue that we're not quite there yet. And I argue that the reason we're not there yet is because of something that I'd like to call the utility gap. And before I demonstrate what I mean by the utility gap, I want to distinguish it from two other concepts that are very widely discussed these days. One of them is the alignment problem, which I assume most of you are familiar with. It's basically the idea that the types of objectives that we optimize these large language models for is very different from what the humans might expect, or might be the kind of objective that humans might be seeking. It is indirectly related to what I'm going to talk about, but it's a slightly different topic. So first I want to distinguish the utility gap from that concept. The second concept is the objective gap. And for those of you who might not be familiar, the objective gap refers to the discrepancy that exists between the pre-training objective of a language model and the fine-tuning objective of a language model. So of course, if you have an autoregressive model during pre-training, you have a next token prediction objective. If you have a masked language model, your model is trying to uncover some randomly masked tokens. But then during fine-tuning, you have all of these real-world tasks, right? As I said, information extraction and so on. So you have to kind of retrofit those tasks to the pre-training objective, and it doesn't always work very well. So this is a real issue, but I'm not going to be covering it during today's talk for two reasons. One is it's a very well-known issue. There's a large body of research around this issue. The second thing is, with the advancements that we saw in large language models in the last couple of years, it was kind of demonstrated that scale sort of takes care of this problem. And so if you have a model that's large enough, has a high enough number of training parameters, is fed a large enough pre-training data set, you don't need to worry about this problem as much. Kind of you can do in-context learning, few-shot learning, all those approaches that are very common these days. In contrast, what I'm referring to as the utility gap is the difference that might exist in the test performance of a model in a clinical setting versus its performing in an actual operational workflow. And this has nothing to do with there being a bug in the model, or there being data leakage, or there being some issue with the way the test set was sampled. This is not necessarily an out-of-domain distribution generalization problem. Even if you do everything correctly in your clinical setting, I argue that things could still go wrong in production. And that's what I'll be discussing today. So I'll demonstrate that to you with an example. Now, if anybody here works in document AI or in the broader context of natural language processing, I am sure you will, especially if you work with operational workflows, I'm sure you will identify with this narrative. So imagine you're a research scientist and you're tasked with building an information extraction model, which is probably the most common task that ops teams deal with on a daily basis. So you basically either create your model from scratch, or you use an out-of-the-box model, or you use a language model. Whatever you do, it doesn't matter. You create a model, you sample some data from an actual production data set, and you test your model on that data set vigorously, and you make sure that that test is watertight, it is very robust, there's no bugs, there's no errors there, there's no data leakage. And you get amazing performance out of that model, 99% accurate. Now, let's assume that magically you don't have a recall problem. So 99% accurate means that of any random 100 entities that your model tags, there's only one false positive. Very precise. So you're happy, you show this to the ops team, they're very excited about it. They say, it looks like this model could save us 99% of our time, which is amazing. So let's put in the investment of time and money to deploy this and to run a pilot. So that's what they do. They deploy it in a lower environment. They pilot it with some of their data on their side. And they come back to you and they say, your model is useless. It is less than 50% accurate and it does not save us any time. So you're very confused. You don't know what's happening. So you tell them, hey, can you ship me a sample of your production data? I'm sure there's something wrong. There's a bug or something that I can figure out. So they give you a sample of their data. You test it on your end. The model's still 99% accurate. So now you're very confused. And you ask them, hey, can I actually shadow you or observe you as you're running this pilot? And they say, sure. And as you do that, you realize something that in hindsight is pretty simple, but that's not necessarily something that you thought about ahead of time. And that's the fact that if you are part of an operations workflow, your workflow looks very much like an assembly line, right? On the one hand, you have a sequence of documents that are streaming to you. On the other hand, you have a stack of documents that you've finished processing. And for every current document that you're analyzing, your job is to highlight certain entities. And the advantage that the AI model gives you is that it pre-highlights all of those entities for you. So you, as the person who's running the pilot, all you have to do is just verify if that is accurate or not. Now, for the sake of simplicity, this is not an accurate assumption, but for the sake of simplicity, let's assume that the entities on the same document or on the same page are IID. Given the performance metric that I gave you, it means that of every 100 entities that you could see in a document, one of them is likely to be inaccurate on average. And if your documents are large enough, we could assume that at least in half of them, there's 100 or more entities. That would mean that at least in one half of the documents that you're dealing with, there's at least one error. But if you don't know where that error is, you would have to still inspect every single entity in the document. And this is where that 50% number comes from. Effectively, that entire document is a failure to you because you can't locate the error, so you have to go one by one and verify all the entities, meaning you don't really save that much time. Of course, it's going to be faster than identifying those entities from scratch, but it's not going to save you the 99% margin that you were really hoping to get. So how do we address this challenge? It's a very common challenge, and it actually reminds me of a really, I'm a big fan of this graphic, that basically demonstrates this challenge visually very well. To be fair, this graphic specifically has been illustrated for large language models, but this is not a problem that's unique to large language models, right? This is just a problem with automation. Any model you have, no matter how vigorously you test it in a clinical setting, is not guaranteed to perform as well in a real-world setting, and it's all because of unknown unknowns that you can't control for. That's just the nature of the game, right? And the solution is not to focus on more and more accurate models, because accuracy, as I said, even if you get to 99.99%, there's always that fraction of a percent of an edge case that you have to deal with. So the real question is, how do we create models that enable us to handle these unknown unknowns when they occur more effectively? And I'm going to be covering three main approaches that we're pursuing in my team to address this. These are not the only approaches that you could take, but from our perspective, where we stand, these are the lowest hanging fruits. One is, of course, better calibration. I think this would be, kind of the obvious answer. You want models that are able to tell the user, hey, I have very high confidence in this particular extraction, as an example for the information extraction example. I don't have much confidence in this other extraction. And you want those confidence scores to align with the actual accuracy of the model so that the people can save time and only focus on parts of the document that might be inaccurate. Second is we need our models to treat documents and navigate them similar to how humans do. And the reason this is very important is not because we want the models to perform like humans, but we want the models to fail like humans. So if the types of errors that the model makes are cognitively very similar to the types of errors a human might make, then a human can sort of, in a bizarre way, identify with the model and then identify where the model might be going wrong. And lastly, of course, we need evaluation metrics and annotation schemes that actually align with the way that human users are using these models and evaluating them. Okay, so let's start with the first one, the problem of calibration. Calibration is a well-known problem in the AI community. It's the idea that, if you have, say, again, an information extraction model, what you're effectively doing is for each token, the model is projecting a probability distribution over all the possible tags. And you want that probability distribution to align very well with the actual probabilities that, say, a human would assign to those tags, so that the human can easily identify if a probability of a certain tag is very low, that actually means that the confidence of the model is very low in that tag. So it's very simple. If you have a certain model output and a true output and certain normalized model probability, you want that probability to align with the actual probability of the accuracy of that tag. And there's a well-known paper by Jiang et al. That came out a couple of years ago that laid out some of the main strategies you could employ to create better calibrated models. And you have three scenarios. In one scenario, you have your own custom trained model that you've trained from scratch. And if S of Y is basically the true probability that you want to mimic, you could encourage that by introducing a softmax loss or a margin-based loss to force those probabilities to have better shape as far as calibration is concerned. If you're using a pre-trained model that you're only doing fine-tuning after the fact, you can still add or tack a temperature-based softmax on top that, again, forces those distributions to mimic the distribution that you're interested in. But as we know, these days, a lot of people are using large language models. So if you have a large language model and you don't have the luxury of fine-tuning it or playing around with it as much, if you have the luxury of accessing the logits of that model, you can still play around with different templates and see which template gives you the best logits, a set of logits or distributions. Great, all three are very viable strategies. They've been shown to be pretty effective in the literature. The issue is, as we know, with certain large language models such as the GPT 3.5 and 4 that we're dealing with these days, you don't even get access to the logits. So it's basically a search in the dark. And I'll cover a bit more about some of the future work that we're doing in this space with regards to GPT. But basically the point is calibration in a clinical setting, again, will only take us this far. So let's look at the second potential solution, which is having a functional model of the documents. Now, I might be a bit biased here, but I do claim that the variety of documents that we deal with in the financial industry is actually quite diverse compared to some other industries. There's a very big fat tail distribution. We can't really say, oh, there's this long tail distribution and 80% of the documents are all financial documents. That is not true. We deal with financial documents for sure, but we also have tons of forms, receipts and invoices, as I said. We deal with contracts in the form of prospectuses, M&A contracts, and so on. We deal with narratives, such as suspicious activity reports that come out of different bank branches. So it's a very diverse set of documents. And if we want to model these documents, we have to work within a certain framework that recognizes this diversity. The second challenge is that a large part of our documents have multimodal nature. Now, I want to make something very clear. Yes, it is true in finance, as in many other industries, that a large majority of documents are actually images. They're not like actual well-formatted PDFs or HTML documents or annotated documents. Why? Because they have to be signed, and usually when you sign a document, you have to scan it. So that makes your document a multimodal object. But even if your document is not a multimodal object, you still can have a very complex layout. And the layout signal is extremely crucial to the way we identify or navigate these documents. So here's an example. I have put 4 different screenshots of 4 different types of documents on this page. None of them are actually scanned. Maybe the one on the left is scanned, but the rest are actually well-formed documents. And I've tried to blur the text as much as possible, so hopefully you won't be able to read anything on those pages. But one of these documents is a disclosure, one is a contract, one is an analysis, and one is a report. So I want you to tell me which one do you think is a contract? A, B, C, or D? Right, so I'm hearing A. You could not read any of these pages, but you were able to tell that A is probably a contract because you probably can see a bunch of signatures on it, right? You don't need to know what the page actually says. If I asked you which one is an analysis, you would probably tell me B, because you could see the table, you could see the graph. So this is how these documents align. And the point again being that layout tells you, and layout plus content, of course, tells you a lot about what a document is about. And you don't necessarily need to purely rely on the text of the document. So speaking of layout and the visual signal, again, we've seen massive improvements in computer vision models and joint text and image models in the past few years. Does that mean that we're done? We're good? We could plug in one of those models and they'll be able to process our documents? Again, I don't think so. And the reason is, even for the multimodal documents that have specifically been trained for document understanding, if you look at the architecture of those models, such as Microsoft's Layout LM, which is pretty much the state of the art these days, their visual backbone mimics the visual backbone of a traditional computer vision neural network that processes open-ended images. And those backbones were designed to exploit certain inductive biases. So for the panoptic segmentation task that you're seeing on the page here, a typical visual backbone would exploit things like continuity of color distributions, contrast, contours, highlights, and things like that. These are all extremely important to computer vision tasks. But when you're dealing with documents, you're dealing with very different artifacts. There's a lot more that you can exploit. The content on the page is quite sparse. The majority of the pixels are basically falling on the background. So color distribution is a lot more skewed. There's alignments, right? There's a grid structure that you could exploit. So there's all sorts of inductive biases that are getting missed by these visual backbones because they weren't necessarily aligned to capture, designed to capture them. And speaking of Layout LM by Microsoft, they actually demonstrated this fact themselves. So in the second version of the tool, it was a massive, well, by those days a standard, it was a relatively large model, and it had hundreds of millions of parameters in its visual backbone alone. And then in the third version, they actually started looking at these parameters. So the blue diagram shows the L2 norm of the parameters in the second version, Layout LM version 2. And there's this kind of almost flat line here on the left-hand side. And those are the parameters that were basically not doing anything. They weren't pulling their weight. They were just, hanging out there. So in the third version of the tool, they looked at these parameters and they realized half of them are useless. So they threw all those parameters away. In fact, they threw the complex visual backbone away and they replaced it with a simple linear projection of every single pixel on the page. So that ended up saving half of their parameters for them. So these are the red parameters in the third version. And they still did as well, if not better, in the majority of the tasks. They did struggle a little bit with more complex tasks, such as complex reasoning, question answering, and so on. So I think the linear projection was a good idea in the fact that it was much simpler than the complex visual backbone, but it didn't get them to the complex reasoning tasks. So we still need a better sort of approach to the multimodal modeling of these documents. So given all of these challenges, what we've done is we've designed what we call a document AI framework, where we try to, given a certain document, we try to profile it. So we try to cluster it into different categories. And depending on what type of category or profile it falls under, we try to employ a suitable approach. So your document could be a templated document. These are usually considered, quote unquote, the lower hanging fruit, in the sense that they have a fixed or dynamic template. If you have a fixed template document, you're dealing with something like a tax form. And tax forms are great because they're fixed, they rarely change. I mean, they do, but not as much. They give you the universe of all of the stuff that you want to extract, right? You know exactly what are all the questions on that form. And all you're doing is kind of looking at the original form, looking at the form that's filled out, and trying to extract all the fields that were already filled out. And for this, you might not even need a fancy neural network. You could use traditional computer vision algorithms that do key point alignments, such as SIFT and ORB and BRIEF, and there's a whole slew of different algorithms that you could try that identify key points on these pairs of documents, and they say, okay, this area seems to be aligned with question number 2 on the original form, so this has to be the answer to question 2. And this is work that was led by my colleague Ji-King Ma. Now, of course, we're never always that lucky. The documents, the filled out documents that we receive, sometimes they're handwritten, there's noise on them, there's skew, there's scans, there's all sorts of stuff that's happening. But as a starting point, this alignment algorithm takes us pretty far in identifying all the key points in the filled out form. But that's not the majority of the documents we deal with. In fact, the majority, if they're templated at all, they have a dynamic template. And dynamic templates are templates that either change over time, or they change across different providers, such as different clients, or both. So on the left-hand side, you're seeing a company filing. This is a state-level registration. It's the same form from the same company, but you're seeing a 2003 version versus a 2019 version, where this form has evolved quite a bit. A lot of the fields are similar, but the layout is very different. In the middle, you're seeing 2 authorized signatory forms. So every company has their own template they usually follow when they disclose authorized signatories with us. Now, these were forms that I found in the public domain because I wasn't able to share any of the confidential examples we have. The real world authorized signatory forms that we deal with can be a lot more complex and a lot more different from each other. And then lastly, there's a concept of forms that change across clients and across time. So if you think about something like the operating segments of companies, each company might have a different set of operating segments. And also, a company's operating segments can change over time, either incrementally or drastically. So in these cases, you can't really rely on the alignment anymore because you would have to encode a very large variety of these forms. But you could leverage some of the functional aspects of these document layouts that I mentioned earlier. So as an example, these are 2 pages that have been sampled from the DocBQA dataset. I'm not sure if you're able to read them, but if you were able to read them, you'd immediately know that these are some form of an invoice that has been issued by a particular clinic. It's the same clinic. Whereas this document C is kind of like a cover letter or a memo, right? So document C seems to be quite different from documents A and B. But if we fed these 3 documents into a flat, multimodal model, it wouldn't be able to tell you that A and B are more similar than A and C because it's looking at the pure graphics, right? It's looking at the pixel level graphics. So they all look equally very different. Maybe there's some slight textual overlap between A and B, but that's the extent of the similarity that you get because the content is actually very different. The numbers are all different. There's more rows in B and so on. So how do we get a model to recognize the functional similarity of these pages in the same way that we recognize their functional similarities? Now, there's work in the kind of layout design space that already lays out the kind of visual or spatial cues that we use to understand models. So of course, contrast is a huge signal to us, contrast in colors, contrast in spacing, and so on. Alignment is a huge cue, of course, for reading things like forms and tables and bullet lists. But we also look at things like proximity in spacing to identify that there's something is a certain kind of block of text, like an address block. And we also look at templates that have been repeated across the page or several pages. So to exploit these types of clues, we've developed a model that we call Graphite, which stands for Graph Neural Networks for Identification, Tagging, and Extraction. So Graphite exploits the grid-like structure of forms. Given a form or a template, it models each token on the page as a node. And 2 nodes are connected if they're horizontally or vertically aligned. And this gives you a very nice kind of succinct model of that page that is also very functional. And the great thing is now you could run all sorts of graph neural network models on this, on Graphite, that allows you to propagate information from neighbors to a given node. And you can also augment the edges with additional information. So if 2 nodes are aligned, you can augment the edge with information about how far apart they are, what is the contrast in their color distributions, and so on. And so this way you could propagate information from neighbors to every node and enrich the representation of that node with information from its neighbors. We have benchmarked internally graphite against 2 tasks. Unfortunately, the colors didn't translate very well on this slide, but basically the left 2 bars and the right 2 bars each refer to one of the tasks. On the left-hand side, graphite was benchmarked against layout alarm version 2 on an information extraction task. Even though it's a fraction of the size of layout alarm version 2, it actually outperformed it. On the right-hand side, it was benchmarked against the vendor solution that we were testing at the time. Again, it's much smaller than the vendor solution, but it was outperforming it on an IE task. But more importantly, graphite gives us the ability to do better calibration. Why? Because now we can model these documents or these pages functionally, and graphite is able to tell us that A and B are much more similar to each other than A and C, because now you're looking at graph similarity rather than textual similarity or visual similarity. So you're looking at the layout similarity. And this is great because now we can easily profile what types of documents graphite performs really well on, and if graphite potentially struggles with the document or recognizes a document as something that's very different from what is seen during its training phase, it can signify the user, it can notify the user, hey, you need to look at this output. So we could do a much better job of optimizing the workflow that way. But that's for templated documents. We also have open-ended documents where there is a template, but this template is pretty much different for every single document. So you can't really rely on the template alone. And some of these are forms that we receive on a daily basis. And a lot of these document understanding models that have been released, they use an objective called mass visual language modeling to process documents like forms. And it's basically an adaptation of the mass language modeling objective, right? So instead of having a plain text segment and randomly masking some tokens, you have an excerpt from a page, you're masking visual tokens on that page. And the model not only needs to recover the text, but also to recover the visual distribution and the spatial characteristics of the text. Now, one of my colleagues, Dongsheng Wang, had this idea that we're kind of missing out on some of the information that forms provide us when we use MVLM. And the reason is, suppose for this particular token, right? This is the value of a particular field. So number one, masking values doesn't give us as much information as masking the keys, because values are a lot more open-ended, right? The key says name and the value could be any name. Moreover, when you mask a value, you're not really doing any work to tell the model, hey, this value corresponds to this field. So the model is still not able to model that kind of relationship in the structure of the form. And he recognized that forms have this kind of key value structure, and they're usually organized into blocks. So this could be one block, one key value pair, or this could be one block, which is a set of keys that are close to each other. So his idea was, what if we blocked or masked everything at the block level and then had the model recover the entire block, and that would potentially teach the model a lot more about the interdependencies of these different blocks with each other. And I'm not going to get into the technical details in the interest of time, but there's other information, there's other kind of architectural details there, like each token is not modeled just in relation to the entire page, but also in relation to all the other tokens within its local block, and so on. And they benchmarked that model against 4 data sets, and all of these are information extraction data sets. They always matched or surpassed the state-of-the-art in terms of performance, but something that's noteworthy here is FundsD and FundsD Plus are a lot more diverse in terms of the types of forms that are involved than Cord and SROIE, because I believe Cord and SROIE are both receipt data sets. So they're like, restaurant receipts and so on. So the format is a lot kind of more consistent across the board. So you see that when the data set is a lot more diverse, our model actually outperforms other state-of-the-art by a larger margin. But again, going back to the calibration point, the added advantage of this type of model is that you can now profile the performance of the model at the block level. So there might be certain types of blocks, such as the name and address block, where the model does very well, and then there might be certain blocks like this one, where the model might not do very well. And then again, we could direct the efforts of the user or the human overseer to the parts or the blocks that the model does not do very well. Now, the most complex type of document that you could deal with is an open-ended document that is what we call a dense document. These are things like financial reports. You could have form-like snippets within dense documents like tables and bullet lists and so on, but the majority of the document is just dense paragraphs. And here you would need a much more complicated approach. Again, Dongcheng Wang from the team started experimenting with kind of a two-pronged approach. So he proposed a model called DocGraph-LM, which has this two-pronged architecture. The upper pathway does the same thing that a lot of these state-of-the-art transformer-based document understanding models do, does masked visual language modeling, all of that. The lower pathway uses a graph neural network to encode pairwise relationships, similar to graphite, but a lot more complex in terms of the objective that he pursues, because not only is he modeling the distance between two nodes, he's also modeling the actual direction, corresponding direction of their placement within that layout. And it's actually, it does not introduce a ton of parameters. You're only getting a small overhead in terms of the number of parameters of the model, but if you tack DocGraph-LM onto whatever state-of-the-art model you deal with, it does offer an improvement even in complex tasks such as question answering, visual question answering over documents. And again, that graph component gives you a lot more explainability and control over what types of documents you want to process and where you want to engage the human, and that's basically the advantage of graphs. Finally, you could have completely graphical pages, and these would be things like flowcharts, diagrams. We deal with a lot of organizational diagrams, supply chain networks, investment graphs, and so on. And this is a very understudied field. I think the models are about to take up this space more and more, but research is still very open. So one of my colleagues, Peter Babkin, he joined forces with some other people to create the synthetic data set that was just released at SIGIR this year. And this is a massive data set of synthetically generated diagrams. And the reason is they were trying to collect data sets in the public domain to train their own models, but they couldn't find anything viable. There were some, I think there was one or two synthetic data sets that came out, but they didn't really reflect the complexity and the rich nature of the types of diagrams we were dealing with. So they used a generative adversarial network to create all of these synthetic examples. It's a very rich data set, probably the most complex I've seen out there. So be sure to check it out if you're interested in this space. They also demonstrated how difficult it is to do something like question answering over this data set. So they split the questions into three categories: extractive questions, yes/no questions, and counting questions. And you can see that the performance, I think this is layout LMB2, the performance of this state-of-the-art model on these questions is nowhere near satisfactory, which attests to the complexity of these diagrams. And then lastly, as I said, we can't just continue using these flat accuracy and F1 metrics when we're dealing with these complex documents, because even though I did mention that for simplicity's sake, we will assume that entities on the same page are IID, that is absolutely not true. And we should consider their interrelationship when we annotate or when we evaluate these models. So Ranz Migrod, who's on my team, he also had this idea. And he started proposing a hierarchical annotation and evaluation schema, especially for forms where this key pair relationships exist, and these key pairs could group together to form bigger blocks, and there's this hierarchical tree-like structure. And he showed two things. One, that his tree-based F1 score, which is an evaluation metric that he proposed, is actually a lot harder to achieve a reasonable performance on than the flat F1 structure that a lot of these papers are reporting. And secondly, he also proposed node alignment metrics and tree alignment metrics to get a better understanding of how these information extraction and relation extraction models are working in the real world, right? Are they actually capturing the complex interdependencies of these different entities, or are they just good at optimizing for certain types of entities? And then lastly, we've also been very active in trying to open source as much code and as much data as possible as we continue exploring this space. I already talked about the data set in the middle, but my colleague Nataraj Raman released a data set of synthetic documents with very complex layouts, I think last year. And if you attended the ADS keynote by Dr. Samina Shah last year, she went into more depth about this data set. It's a very interesting data set in the sense that the layouts are all sampled from real world examples, but then the text is sampled from random novels and pages online. So whatever model you build that has to tackle these documents cannot rely on the text. you're forced to learn the layout of the document. So this is a very interesting and challenging data set. And we're also working on a pretty sizable enterprise document data set that is probably going to be the most deeply annotated and the most diverse set of enterprise documents that's out there. It's about to be released, so if you're interested, send me a note and I'll be sure to share it with you once it's released. So that was the kind of general framework within which we'd like to function and within which we'd like to explore the document understanding space. Some of the current and future directions that we're exploring at the moment. One is end-to-end generation. Now, if you remember in one of the earlier slides, I mentioned that we're usually not lucky enough to get very clean forms and documents. There's a lot of handwriting on the documents. So we sometimes have to rely on handwriting recognition models, which can be inaccurate. Even when we don't have to rely on handwriting recognition models, as a first step in processing these models before we feed them into a multimodal model is you usually have to use some form of OCR. And of course, OCR tools all come with their own error margin, and that error propagates through the pipeline, and there's all sorts of issues that arise. So recently, in the past couple of years, there has been some studies around end-to-end document understanding where you don't need to use an OCR engine anymore. The model is treated as a visual artifact directly. And two of the well-known examples are Donut and UDOP. We're hoping to get into that space as well, but again, with an eye to the functional characteristics of the document. Because again, if you want to throw away the OCR, you could treat the page as a visual artifact and as if it's an image of a cat and dog, but we know that that's not true. So you should try to leverage the kind of sparse signal and the grid-like structure as much as possible. So we'd like to focus on a graph generation technique to see if we could generate the corresponding graphs of different documents. The second direction is, if you recall in the calibration slide, I spoke about how difficult it is sometimes to focus on calibration when you literally know nothing about what's happening under the hood in a given model, such as GPT 3.4, 3.5, or 4. And my colleague Nataraj Rahman, he published something at AI Stats earlier this year. His study was not focused on calibration, it was focused on counterfactual sampling for, say, explainability or fairness and so on. And he proposed a hierarchical Bayesian model to do effective counterfactual sampling for both categorical and continuous variables. And we're hoping to take inspiration from this study and kind of expand that to potentially do a search in the text space when we are trying to fine-tune prompts that give us better calibrated outputs. So more on this later. It's still a work in progress, but again, if you're interested, feel free to reach out to me. And lastly, I talked a lot about the visual signal and the multimodal signal of these documents, but of course, us being in finance means that we deal with a lot of quantitative reports. And no quote-unquote document understanding model is done before it actually understands the quantitative content that is being disclosed in these documents. So in conjunction with CMU, we've released some papers in that regard as well. These are some of the papers of the work I did with Dr. Carolyn Rose at CMU on how we could improve generalization and especially compositional generalization when it comes to quantitative reasoning over these documents. Again, if you're interested in this field, feel free to check them out and reach out to me. And with that, I'm going to wrap up my talk. Thanks again for attending, and feel free to ask any questions here, or if you have follow-up questions, feel free to reach out to me via my email. Thank you.